And there we go. So this presentation is an activity called Discovering Plate Boundaries. Some of you might be familiar with it. I have a disclaimer that I will share in a moment about where this activity came from. But first, I would just like to introduce myself. I'm Andrea Williams, and I teach in the West Bloomfield School District. I have taught there for 17 years, and during that time, I have mainly taught 6th and 8th grade science. So I've taught a little bit of everything, but my heart and my love is in earth science. So I especially love the inquiry-based earth science activities, which are sometimes harder to come across. And I am currently the MESTA treasurer. I've been with MESTA for probably 6 years now, officially as a board member. And I will, by the end of the presentation, I will put the link to these slides into the chat if you're interested in that, because there are some links inside the slides to some outside sources. So I would, since we're such a small group, if you don't mind, if you wouldn't mind unmuting yourself, and if we could just go around and say who we are and just basically where you, maybe where you teach and what grade level or what your role is in education. That would be okay. Maybe we can. I see Amy has unmuted herself. Go ahead, Amy.
Yep. My name is Amy Cummings, and this is my 14th year teaching earth science. I currently am doing 6th and 8th grade earth science.
Nice. Just like me. And
okay, my name is Jen Dieters, and I am doing my student teaching right now at White Cloud Public Schools, and I am with 6th and 7th graders.
Okay, thank you. Good. Middle school compatriots. How about Tammy or Mindy or John?
Hi, I am Tammy Bravo. I work for IRIS. I actually am a seismology outreach specialist.
Yes.
So
Oh,
work
boy.
more on the development side. I used to be a middle school teacher. I've been out of the classroom for probably so long now that no longer counts. But
well, Tammy, if I get anything wrong in this presentation, you feel free to chip in.
I am Mindy Woodworth, and I'm actually a student in the elementary education program at KVCC right now, and looking to transfer to Western in the fall. And I preferably like to teach 1st through 3rd grade.
Nice.
Hello, I'm John Niedermeller. I teach introductory geology at Wayne State University.
Nice. Thank you. Well, thank you for making me now feel like there are actually people in the room instead of just little boxes. So welcome everybody, and we'll dive right in. So here's my disclaimer. This is not my original activity. This is an activity that was created by Dale Sawyer at Rice University. It is free on the internet. You can support him by, there's some maps that you use for this activity, and I believe you can purchase big sized color versions of these maps and other supplies from him. But it's a great inquiry based activity, and I have done this with students. And the first time I did it, I was concerned that it would be above what they were capable of, and I was pleasantly surprised to find out what they could actually discover through this activity. So I can give you the perspective of someone who's taught it with students and share the activity with you, and give you those insights that I have from kind of shaping it a little bit for the middle school audience, so and middle school students. But it is something that middle schoolers can do, and it's just amazing how going through this process actually helps them to come up with the plate boundaries that are labeled and recognized by the scientific community without any pre-knowledge of tectonic plates and plate boundaries. So I am excited to share it with you, and hopefully it's something you'll be able to use. So being from Michigan, being Michigan teachers, you're familiar with the NGSS, and basically the way that we want to present and engage students in science now fits right along with this activity, because we want our students to really be able to master subject matter at a deeper level and not just know facts, but to develop that scientific reasoning and scientific practices and thinking like a scientist. And we want our students to also develop practical skills like critical thinking and collaboration, those 21st century skills that we all know employers are looking for nowadays. We also want them to develop an interest in science and learning about science, not just memorizing science facts. And we want them to be able to do science and apply content. So this activity really gets at all of these things that we want our students to be able to do. It really pushes them to think about the data that they're presented with and to do science rather than having science done to them. So I am in love with this activity. In the Discovering Plate Boundaries activities, students will learn, and these are aligned with NGSS performance expectations, but they will learn where the Earth's tectonic plates and their boundaries are located. They're going to have a sense of what's occurring at different plate boundaries. They're going to understand how Earth scientists classify the plate boundaries into those traditional categories that we know of: divergent, convergent, and transform. But they're going to also have a sense of how scientists have come to classify those plate boundaries, because they're going to walk through a process that simulates the classification of those boundaries. And they're also going to get an understanding of how science is not done in a vacuum. It's not one guy in a lab figuring things out. It's not one field that figures things out. And most areas of science, multiple fields of science have to, and scientists have to come together to collaborate, to build understanding from data for these bigger ideas. So through this process, students are also developing a conceptual model of what's happening at plate boundaries and how that is associated with these different features in the land that we see, because they're analyzing data about the features. They're also going to, as I said, develop their critical thinking skills. And overall, this activity leads them to a deeper understanding and more enduring learning about plate boundaries and tectonic plate activity. I will go through all of the pieces of the activity, but the logistics to prepare, you do need to have the special scientific specialty maps, which I'll show you in a moment, that have the data in them. And if you can get large versions of them, because you're going to, and spread them around the room, because you're going to have kids kind of congregating around them in groups to be able to look at the data. I did not take the time to modify this for a virtual setting, but I'm sure that you could do that as well in breakout rooms and provide students with images of the maps if you are currently in a virtual teaching mode. The activity itself throughout is a jigsaw activity. So there are scientific specialties, which are volcanology, seismology, geochronology, and geography. And then there are also tectonic plates that students will eventually be assigned to. So I believe there are 10 of them identified. Well, I'll show you those in a moment. But when you break out the students, they're going to need to be assigned to as a specialist and also a tectonic plate. And essentially, you want to make sure that you have, for each of the tectonic plates, there are 4 specialists, 1 from each of the categories. That'll make more sense when I show you the list of the plates and the specialties. And then each student will need 2 copies of a plate boundary map. So this is the plate boundary map that is used in the activity. And then these are the plates that are identified that students would be assigned to, and the scientific specialties. So one way of thinking about jigsawing this out is that if you had a class of 24 students, don't we all wish that's all we had? You would have 6 plates, and then each of those plates would have one of the 4 specialties assigned to it. So the student might have as their grouping that they're assigned to North American plate and volcanology, or North American plate and seismology, etc. If you have any questions at any time, please jump in. This virtual presentation sometimes makes me feel like I'm talking to myself. So please feel free to chip in or turn your video on so that I know you're there. So these are the specialty maps that students are presented with. And this map in particular shows us the seismologist specialty. And so we have data on earthquakes from 1990 to 1996. And I'm just going to scroll through these a little bit, and then I am actually going to have you kind of engage with me in one of the maps. So this is our volcanology specialty. So this is the map that students would be engaging with in that specialty. And this is the geochronology map. So students in this specialty are focusing on the seafloor age. This is a pretty one. And then our geography map, where students are focusing on elevation, both above and below the ocean. So there's 3 parts to the activity, and in part 1, students are making observations with their specialty. So they are dispatched to examine the data for their scientific specialty, and they're encouraged first to just consider the data worldwide. I always clue them in before they begin to classify and look for patterns to make sure that they have a sense of what the data is showing them. If you've worked with students, middle schoolers especially, a lot of times they just look at the pretty colors and they forget all about the key on the side. So I kind of guide them to make sure they check the key to see what they're actually looking at in the data, and then to start looking for patterns. Patterns they might look for in the so there's point data, and then there's the color-coded data with the highs and lows. So they you might give them a few kind of tips on what to start looking for to get them thinking to start with. So in part 1, they're really just kind of looking at the data, making sense out of it, and then kind of talking with other specialists that are at the same map with them about what they're observing and what patterns they might be noticing, or what they're wondering about the data, or what's surprising, etc. And then for the second part of task of part 1, they're going to be directed to focus more on the boundaries themselves, which are marked on the map. And then they're going to have to start thinking about how they might categorize different boundaries based on patterns in the data. So they might classify those into up to 5 categories and find different places where there are boundaries that fit into those categories. And of course, as task 3, then they're going to color code their plate boundary map to correspond with the categories that they have created, and create a key that includes a detailed description of how they've classified each of the boundary types. So I thought it would be fun for us to give this a try as students. So you might already know a lot more background information, particularly Tammy, than students would come in with. But if you could sort of put a student hat on and unmute yourself, and we could just talk a little bit about what do you notice about this data? We're going to focus in on the seismology map. What patterns might you notice?
I noticed there is a lot of red dots, which are shallow earthquakes in the oceans.
Thank you, Amy. Anyone notice any other patterns?
That the deepest green and blue colors are not found very widespread.
Thank you, Tammy. Any other patterns that you notice?
There are a lot of earthquakes around the edges of the continents on some of the coasts.
Thank you. Do you notice a correlation between the earthquakes that you see on the coasts and depth, or no?
Depends on the continent. In South America, it's deeper, but in North America, it's shallower. Eastern edge of Asia is deeper.
Okay, thank you. So moving into thinking about actual plate boundaries, so students would have their boundary map and they could see where the boundary lines are marked on that map, and they would think about what's happening at different boundaries. And this is where they would start to classify based on patterns in the data that they're observing. So if they're struggling to start with, one thing that I've done to help them is to kind of point them into a certain place to look. So I might start by having them focus in on the North American and Eurasian boundary and have them thinking about what's going on there, and then see if they can find similar activity in other places on the map. If you notice any similarities in boundary edges, would you be willing to share those with us? Anybody see anything that we might be able to classify as a type with a description that we can find in different places? I think that Amy mentioned that there were shallow earthquakes in the oceans.
Yep, down like along the Mid-Atlantic Ridge and the western edge of the Nazca Plate, but I know I'm not supposed to know that stuff yet. So as a student. But
So
yeah,
as
so
a student, we might just observe that there seems to be these lines of shallow earthquakes in the ocean. And students might recognize that as a category that they could call, say, type 1. And then they could describe that as narrow lines of earthquakes that are under the ocean. And then they could mark their plate tectonic map with a color for where all of those fall. Some other patterns, and I think Amy noticed this too, are these coastline earthquakes. So students might recognize that in some places on the coastline where there's large clusters of earthquakes, they're mostly shallow, and they might label those as another type and color code those. And then, as you pointed out, Amy, there are, or was it Tammy? There are some coastlines where there's some shallow earthquakes, but then there's deeper earthquakes. So they might label those as another type and category.
And there's no earthquake.
Oh, I'm sorry, John, go ahead.
And there's no earthquakes along certain continents' edges.
Yes, so it's also important for them to notice where there's no activity happening. Of course, students don't have the terminology of divergent, convergent, and transform yet, but the things that students are observing, those patterns in the data are going to lead them to grouping and classifying the plates in a similar way to the scientists who used the data initially to understand what was going on did. And it's fascinating because when I first did this with 8th graders, I thought there's no way. There is no way. And there is. They do it. So at each of these specialty maps, students are kind of going through this. And my role as the teacher during this time is just to kind of flip between groups and listen in and drop questions in to get them to talk more about things they're observing. Maybe if they're really stuck and struggling, to guide them to a starting point to get them to think about what do you see here and do you see that anywhere else, to help them with that classification process. But really without giving them, giving things away, just kind of guiding and facilitating them towards their own discoveries and aha moments as they're working with the data. And so working through tasks 1, 2, and 3 of this process, they start by just observing the patterns in general worldwide, and then they zero in on the plate boundaries, and then they color code their maps. So here's an example of what, and I know this little print in the legend is hard to read, but this was actually included with the materials, this sample, because I didn't have a student sample of my own to share. This sample is included in the Discovering Plate Boundaries materials that you can access through that website that is in the slides, which I'll share with you. And so this is a sample that's right in there, and you can see what's in the descriptors a little better in that. But this is just an example of a product that students would end with. So they would have up to 5 boundary types that they have color-coded worldwide on the map, and then they've described the characteristics of their data that are found at those boundary types. And they are encouraged, as John pointed out, they are encouraged to include areas of no data or no little data in their map. So that's their type 5 here. So they have labeled in this one those shallow earthquakes in the ocean. So that's their type 1 boundaries. So all earthquakes are shallow. And then they've noticed some other things here too. So far, so good. This is a close-up of one of the boundary types of a student annotated boundary type, just to, still hard to read here, but essentially they're color coding what they are noticing as similarities in patterns in the data. So part 2 of this activity is kind of putting it all together. So now they've become a specialist in a certain area, and then they're going to come back and meet with their tectonic plate group. So for example, the North American Plate Group will now have 4 people meeting who each have a specialty, and each are bringing a piece of the puzzle to put together into a full understanding of what's happening at these boundaries. So there's a volcanologist, a seismologist, a geochronologist, and a geographer. And they bring what they know. And so the first thing they're going to do together is to visit each of the specialty maps in the room. So they're going to do a little gallery walk and share of what they came up with for their color coding and classification. So each specialist will brief the other scientists and share with them, this is our data that we looked at, this is the information it was showing us, and these are the classifications that we came up with. So they go through that at each of the specialty maps, and then they're going to work on putting that data together into a new classification system. So they're going to all share the classification system they came up with, and then kind of combine what they did into a system that incorporates all of the data in the classification and create a new color-coded key to shade the new boundary classifications that they've determined. So it might make a little more sense if we look at some examples. And again, I apologize, I know you can't read the print that's down here, but what is showing here are just focusing in on the African plate and the boundary types for each of the categories, each of the specialties, as they were coded in some student exemplars and samples. And what students would kind of walk through a process of doing is finding if what is happening in each of the specialty areas at certain points in the boundary. So for example, they might identify that this section of the African plate, which has all shallow earthquakes, also has, your little pictures are over my color-coded key here, also has, get out of the way. Sorry, my technology, my Zoom toolbar is in the way now. Also has little or no volcanic activity. That's what this color-coded category identifies. And then it also, from the geochronology expert, it is surrounded by younger rock, and there are some peaks here. So they might put all that together and say that this section of the map is type A and it has these characteristics. And then they can identify that there are other sections of the map that also match that category. What questions might you have about that? I just want to make sure I explain that in a way that made sense. So part of a product they might come up with, this would be showing the type, boundary type A. They might identify that these sections that are now highlighted in yellow are sections of the African plate that incorporate these features of each of the specialty data. And if you're savvy, you might notice that these are also features that occur at divergent plate boundaries. So they've identified boundary type A without naming it yet as a divergent boundary. If I'm going too fast, let me know. In part 3, they're going to make their findings public and then make some connections. So they would choose a spokesperson or two from their team to describe the plate boundary classifications that they came up with and share with the rest of the class. During this time, as the teacher, I'm using some questioning to get to draw more out of them. I'm using some questioning to have them start to think about some connections. So different teams might have identified similar patterns around their boundaries and classified them. And so we can start to see that, oh, this category that the African plate team has called type A with shallow earthquakes and few volcanoes and young crust and some mountain chains, that also shows up around another plate boundary. So we can start making some cross connections between different plate boundaries, and that we've started to identify some commonalities worldwide in types of boundary descriptors. And then, so this is kind of following the activity before concept, concept before vocabulary method. If you've ever heard of that, they refer to that as ABC, CVV, where students have done an activity with some data. Now they're starting to put together the vocabulary and the concept and the vocabulary. So they're going to then look at some sources that they might read some text, they might watch some videos, they might interact with some simulations that describe and show what scientists in the scientific community have agreed upon as far as plate boundary classifications, and start to see the vocabulary, divergent, convergent, and transform, and they can start to match that up with the categories that they have come up with. So here's where the a deeper understanding is coming in, because they've actually discovered something that they're now going to attach a vocabulary term to, versus being presented with a vocabulary term that they're then just going to memorize the characteristics that go with it. They've actually uncovered that there are areas where there are shallow earthquakes and et cetera, like in the African plate. And now we can call that a divergent plate boundary, and we can start to make connections that that activity makes sense because of what is happening as the plates separate. So they're starting to uncover and connect the information to what they've already identified.
I have a question.
Yes.
Would you teach the cause of the plate motion prior to this or after it?
So I have done it both ways, and I think that it makes more sense to do it afterwards, because we're first identifying, and that kind of follows historically what was happened, because there was a recognition that plates were moving before we understood exactly what the mechanism was. So,
okay.
Yeah. And I think it makes a little more sense once they know what's happening in their, as they're putting those pieces together in their understanding and the model that they're building in their mind. It makes a little more sense because, well, they have an idea that these plates are going in different directions and they're coming together. And then when they put the movement of the magma with that, it just makes,
Because right now, like I'm teaching continental drift right now.
yeah.
With all the evidence and everything. So I'm like, I'm
Yeah.
coming up to this in a couple of weeks, but typically I do continental drift and then seafloor spreading. And then I go into the plate tectonics.
Mhm.
Should I skip the seafloor spreading and just go right from continental drift into like an activity like this? Because seafloor spreading, I show them the ages of the ocean floor and they make the connection that it's younger at the mid-Atlantic ridge and it gets older, you know? So it's like, they're already looking at that. So should I like
Yeah.
not do the seafloor spreading?
I think you could, when you do this activity and they put the labels on, then you start to talk about the mechanism for movement, and the seafloor spreading is part of how we understood the mechanism of movement, because that's where the magma's coming up. So you could roll it into that explanation of the mechanisms.
Okay.
That was one of the pieces of evidence that helped in the understanding of the processes that were happening. If that makes
Okay, thank you. Yep, thank you.
Yeah. I love this activity. Are you face-to-face right now so you could do this live? Or?
No, we start Monday face-to-face. I've been virtual for
Yeah.
5 weeks, but we have every class every day.
Oh, good luck. Oh, I'm so sorry.
And well, that's how it was virtual, and starting Monday, I have classes of like 32. So I'll have every class every day starting Monday.
So
I'm
social distancing just goes right out the
Yes.
window.
Well, and I'm texting another science teacher at my school because we use Schoology. I don't know if you guys know what Schoology is.
Yeah.
But so like instead of using Zoom, we do conferences through Schoology, which is this like a Google Meet basically. But we can do breakout rooms. And so I'm asking him if the kids have earbuds in, could I put them in breakout rooms so they could still look at the map and talk with people around the room?
Oh my God.
Would that work? So I'm wondering if that will work. He said there might be an echo, but I'm hoping it will work. They all just sit with their earbuds. They can talk to each other from across the room. I'm hoping.
That's brilliant. I'm going to have to touch base with you to find out if that we have half the kids in the morning and half in the afternoon face-to-face. So I have smaller sections, but they still have to talk to each other from across the room. And so I've just got kids collaborating by kind of shouting who's 6 feet away from them. So part of this whole process here in helping them is the facilitation of the discussion. And so as we're reading about from these sources and watching videos and making these connections, we're having class discussions about the understanding and the connections that we're making. So I would keep all of their materials throughout this, their boundary maps and their category, for their plate boundaries and their classifications for their plates, and have them keep coming back to those and making connections between those two. So do you see places here that match up, and facilitating that discussion so that they can make those connections and solidify that understanding. So I'm going to talk a little bit more at the end about strategies for facilitating productive discourse with students. That could be a whole nother workshop, so I probably won't be able to give you all of the tools and strategies that I have, but we'll touch on that a little bit at the end too. So this is just from my experience. These are some of the patterns that students have been able to make connections with. So they can actually find places on the map that they will classify that we can later identify as convergent plate boundaries with the ocean interaction, the land and land interaction, and land and ocean plate interaction. So they might have categories described by these. They won't use the word arcuate, but they might say, they might notice that the arc shape of the Aleutian Islands and the Japanese islands as a part of their descriptors. Sometimes they don't, but they will definitely find those places where their plates are showing deep trenches and deep earthquakes and lines of volcanic activity that can then be connected up with, well, this is a convergent plate boundary. And then we start asking the questions of, well, why why do we see these things here? And when they start exploring the movement of the plates and the subduction, then they can start making connections like between the activity that's happening and the motion of the plates. It makes sense that there's going to be a deep trench, that there's going to be deep earthquakes because of that subducting plate. And they can actually, in some cases, some students can actually identify by going back to the data that the earthquakes are on the, Tammy, correct me if I get this backwards, are on the side on the plate that is overriding. Is that correct?
Say that one more time.
The kids can actually identify on the maps when they're talking about these different plate boundaries that earthquakes show up on the overriding plate.
There are definitely earthquakes on the overriding plate, but as well on the subducting plate.
Yeah.
So depending on where it aligns with, you had a topography map that they can see that it'll actually end up being on both sides, but their patterns will be a little different.
Yeah. Yeah, and the deeper earthquakes are on one side versus the other. So some of the students will actually begin to see those things. And if you ask questions that facilitate leading them towards that, you can help them bring that out too as well. But it helps them to understand the actual movement of the plates by making these connections with the data that they're seeing in the patterns in the data. These are some images that are taken. These come from the Discovering Plate Boundaries website, but it just shows a comparison of all of the data sets at different exemplary plate boundary locations so that you can kind of see those patterns. So we have the earthquakes here with the shallow earthquakes. I believe that is the subducting plate. Yeah, on the subducting plate side, and the deeper earthquakes on the overriding side, and the trench that shows up on the subducting side, and the fact that at the convergent boundaries, there is not really a distinct pattern in the age of the rock. So there's also, here's one for convergent plate boundaries to land plates with all of the dispersed earthquakes, the high mountains. And then we have our ocean land subduction plates, subduction plate boundary, convergent plate boundary. So students will actually, through discussion and sometimes just with their own critical thinking skills, find these patterns that really distinguish the different types of plates. So same thing for divergent plate boundaries. We used that as an exemplar earlier. And then here's an image showing the different pieces from the specialty maps together to show how those characteristics come together into a classification. Oh, and I don't know why I put that back in there. Oh, because that was so this is the area we were looking at on the previously when we came up with that classification. And then transform, those are a little bit trickier for kids. They can identify them, but they're not as distinctive in the patterns in the data. So they vary a little bit more. Questions, thoughts, comments so far before I talk a little bit about talk moves?
When you give the kids, oh, sorry, go ahead.
Sorry. Do you find that any of the specialties struggle with the maps more than others?
Yes. I think probably the elevation map is one of the more difficult ones for the kids. I think because it's above and below sea level, they can get the idea that it's deeper if it's negative, but I think that throws some of them. That's probably, and the seafloor one, they see the patterns, but I'm not really sure if they understand the, like the, what it means to say younger and older rock when they're looking at it. But probably the topographic one is the most difficult for them. And then just strategies as a facilitator, I'm making sure that as I'm walking around, you know, after you do things a certain amount of times, you kind of know what questions kids need you to ask them to get them to think about the right thing. So I'm walking around and dropping questions and listening in and those kind of things.
My question was, when you give the kids their plate boundaries, so like
Yes.
one kid, you know, one group has like the South American plate. Are they're doing the entire rim? So they're doing like the deep earthquakes and stuff on the western edge and then the mid-Atlantic ridge on the eastern side.
Yep. So like
Okay.
the African plate, they would go all the way around it and then labeling all of the sides. Yeah. Yeah. Has anybody had the opportunity to see the Talk Science primer from, I don't know what TURC stands for. A lot of the, I think if you've done NGSX training, they referred to the talk moves in the NGSX training. But this is a real good resource for developing strategies for facilitating productive talk with students. This is what they have listed in the Talk Science primer as goals for productive talk, or things that you like, beliefs that you have, and the way you organize your classroom to facilitate productive talk with kids. I think for me, some of the really key points are the well-established ground rules. So whenever I have dialogue with kids where it's a class discussion, when I can, I mean, obviously in pandemic times, we can't move around as much, but when I can, we actually organize ourselves into a circle meeting. So we are all seeing each other, we're facing inward. If we have some kind of data that we're sharing, I use big whiteboards for us to put that on a lot of times, depending on what the data is. In this example, we wouldn't necessarily be able to, or in this activity, we can't do that because we're using our maps that, and I guess kids could transfer their maps to a big whiteboard, but I usually have just used the overhead, the Elmo, and have had them put their map in when they're talking so they can share that with us. But we need to be able to see their thinking as well. So they've worked with a smaller group, and then they have something with them that they can refer back to. If you've ever had training in Socratic seminars, usually those are presented for like English language arts, and there's a usually a text that kids are referring back to. So when we do this with science, we're referring back to our data. We're always referring back to our data. But establishing the ground rules for kids is really, really important, and making sure they understand the purpose of the talk is to help us all come to a consensus together on our understanding, and we're building our learning together through this dialogue. And for me, having a clear goal of what is the learning that I want kids to take away from this. So in this activity, when we have our dialogue at the end, after they've had their they've shared their categories for their boundary maps, and then they have had some time to digest some of the understanding from what the scientific community has defined as the different categories, plate boundary categories and characteristics that are happening there. And we're kind of trying to put all those pieces together in our discussion. My main goal is to help them see those connections between what scientists say is happening at divergent and convergent and transform boundaries and what they labeled in their map. So I'm always trying to guide the conversation and keep it focused on, do we see those things in our data in the way that we've classified it? Do we see connections between what scientists have identified are happening at those boundaries and what these features are presenting as. So does it make sense that if something is subducting under something else, we would have deep earthquakes and volcanoes, and kind of knowing for myself what I want them to get out of it helps me to keep the conversation focused with my questioning that I'm using with them, and also guiding them back towards the data so that they're always referring to the data. Kids naturally want to speculate about things, but we keep saying, well, is that shown in the data? Is that reflected in the data? Can you find evidence to support what you're saying from the data? Is important and helpful. The talk moves themselves, there's lots of different talk moves, and I apologize for the tiny print again, but this is also in the Turk Talk Moves primer. But this is a summary of some strategies that you can use within the conversation to get kids not only to talk, but also to talk to each other. And that's been my ongoing goal, is to get kids to talk with each other, because a lot of times when we have class discussions, they just want to talk to me. And so it ends up being this little kind of tennis match where I'll ask a question, somebody will talk about it for a little bit, then somebody else might put in their 2 cents, and then somebody else might put in their 2 cents, but the kids aren't really cross-dialoguing with each other. So my favorite talk moves are the ones that in the goal that's labeled Students Think with Others, 7, 8, and 9, and also number 4. So getting them to listen to each other, and then getting them to question and think with each other. So asking them, not only do you agree or disagree, but why do you agree or disagree? So can someone speak to what you heard somebody say, and what you agree with that, or why you have a different idea? Can someone add on to what someone is saying? Can someone explain what you think the person who just talked means? So those kind of questions really cue them in to really listen to each other, and then to really engage with the ideas that their classmates are sharing. So I have these talk moves with me whenever I'm in a discussion and dialogue with kids, to remind me of what kind of things I can ask. And then I also provide the students with some questioning stems or talks, sentence starters that they can use when they talk with each other, to help them in that respectful dialogue piece, especially the middle school level. They need that. They need to, the kind of the help and guidance to be able to say to someone, I disagree with you because, rather than that's a stupid idea. So this has been an invaluable tool for me. And the link, I do believe in the notes for the presentation, I put the link to the whole Talk Science primer, but it goes through some examples and it gives other explanations and strategies in there. And that's really all I have. So if you have any other thoughts or questions or feedback or any wonders, or want me to tell any stories?
In our geology lab, a lot of times we use to look at the sea floor spreading, how fast the continents are moving.
Ooh, yeah.
So what we'll use is 2 maps, distance maps, and the other one's the age of the floor maps.
Yeah.
That they can calculate how fast the spreading's going on.
Yeah.
Maps.
That's really cool. I had I've done an activity with my kids that tracks the movement of Hawaii and the hotspot under Hawaii, where they graph to find the movement. I think it's based on the age. It's been a while since I've done that one, but that's a neat one to think about the rate of movement of the plates too.
I always explain, I think they get they can't understand when I point out that the plate directions can change And when you use Hawaii and you can show at one point
Yeah.
it was moving one way and then and they're asking, well, what caused it? And we have no idea.
Right?
No, it happened.
Maybe you'll figure that out someday. Yeah, I just absolutely love this activity. And like I said, even I haven't done it with younger than 8th grade, but I've done it with 8th graders, and I was just amazed. I mean, I did not think they would find these same categories, and they really did. And it's incredible. So, I might have to put the
This is informative. Thank you.
Thank you. Yeah, I will put the link in. I think we're going to get pulled out of here before I can get it into our chat. So I'll put it in the chat in the main room if you want the link to these slides. So, yeah, thank you guys. I was worried that I was up against the presentation for the field trips that I wouldn't get anybody. So I appreciate you being with me. And here comes the hook. We always get the hook, the abrupt pull back once the timer goes off.